All right, so far we've taught a computer how to predict a number, right? Something like the price of a house. But what happens when the answer isn't a number at all? What if it's a choice, and the stakes are, well, life and death?
I mean, think about it. Imagine you're a doctor, and you've got all this data about a patient's tumor, its size, their age, whatever. The computer needs to make a simple choice with huge consequences. Is it malignant or is it benign? Suddenly, we're not predicting a price anymore. We're trying to predict a category.
And that's the big shift we're making today. We're stepping out of the world of regression, where the answer can be any number on a smooth line, and we're jumping into the world of classification, where the answer has to be a specific, distinct label.
The official name for this is binary classification. Binary just means two. The computer only has two choices. Is this email spam or not spam? Did a student pass or fail? And for us, the big one, is this tumor malignant or benign?
So your first thought might be, hey, wait a minute, can't we just use the tool we already have for this? It's a really good question.
I mean, why not just draw one of those straight lines from linear regression and, I don't know, set a rule? We could say if the line's output is over 0.5, we'll call it malignant. If it's under, it's benign. Seems simple enough, doesn't it?
And you know what? If you have a really clean, simple set of data like this, it actually works surprisingly well. Look at that. The line slices right between the two groups. Our 0.5 threshold correctly separates every single case. So far, so good. But watch what happens now. We add just one more data point. It's a very large tumor, so it's obviously malignant. But because linear regression is trying its best to fit all the points, that one new point forces the entire line to tilt. And just like that, our simple 0.5 threshold is now in the wrong spot, and it starts misclassifying tumors that it got right just a second ago. It turns out, straight lines are just too sensitive, too brittle for this kind of job.
So, if a straight line that can shoot off to infinity is the problem, we clearly need a totally different approach. We need a model that doesn't just think in raw numbers, but one that thinks in terms of probabilities.
Let's put our old tool, linear regression, side by side with our new one, logistic regression. The differences are huge. Instead of spitting out any old number, logistic regression gives us a probability, which is always neatly tucked between 0 and 1. And visually, we're swapping out that fragile straight line for this much more stable S-shaped curve.
Now, this S-curve has a cool name. It's called the sigmoid function. The best way to think about it is as a kind of mathematical squishing machine. You can feed it any number you want, positive a billion, negative a billion, it doesn't matter, and it will gently squeeze that number down until it fits perfectly between 0 and 1. And that, of course, is the perfect range for probability.
And this right here is the absolute key. The model isn't just giving us an answer anymore, it's telling us how confident it is in that answer. It's communicating the likelihood of something happening.
So let's make that real. If our new model looks at a tumor and the S-curve spits out the value 0.7, it's not saying the price of the tumor is 0.7. It's saying, based on the data I've seen, I'm 70% confident that this tumor is malignant. That's a way more useful and sophisticated answer, isn't it?
Ultimately, what the algorithm is trying to learn is something called a decision boundary. You can think of it like an invisible fence. The machine learns exactly where to build this fence in the data so that on one side of it, everything is benign, and on the other side, everything is malignant. That's the real goal.
But this is where things get really fascinating. Finding that boundary isn't a one-size-fits-all problem. It turns out there are a couple of different philosophies, if you will, that a machine can use to figure this out.
Yeah, these two philosophies represent two completely different ways of thinking about the problem, and they lead to two major families of classification algorithms.
Okay, so on one side, you've got discriminative models, like the logistic regression we've been talking about. The analogy here is building a fence. It looks at all the data together, the benign and the malignant tumors, and its only goal is to find the single best place to put a fence to separate them. Simple. On the other side, though, you have generative models. The analogy here is studying blueprints. This approach is, well, deeper. It studies all the malignant tumors by themselves to create a perfect blueprint for what a malignant tumor looks like. Then it does the same for the benign ones. So instead of just drawing a line between the groups, it tries to understand the very nature of each group. When a new tumor shows up, it just asks, okay, which of these blueprints does this new one look more like? This also means it can spot something that doesn't really fit either blueprint and flag it as a weird anomaly. The fence builder can't do that. It just knows which side of the fence you're on.
Phew, okay, we've definitely gone through a lot there.
Let's take a second and boil this all down to the absolute must-know essentials.
First things first, classification is for picking categories, like yes or no, not for predicting continuous numbers. That's job one. Second, the real magic behind logistic regression is that S-curve, the sigmoid function. It's what turns a raw prediction into a stable, reliable probability that isn't easily fooled by outliers. And finally, you have to remember the limit here. These models are basically drawing straight lines or flat planes. But what happens when your data is all tangled up and can't be separated by a simple line? Well, for that, we're going to need an even more powerful tool.
So we've done it. We've successfully taught our machine how to make a choice, and a pretty important one at that. But all of this was based on numbers in a spreadsheet, like tumor size. How do we take the next leap and teach a computer to just look at an image and know that it's seeing a cat? We'll get into that next time.